Today I start on important topics related to vector space. Okay, we know about that vector space plays important roles, and we also discuss vector space and obviously the example of vector space. Okay, today I start from subspace. Okay, all are known about it. Subspace. We also discuss this subspace today. Okay, also going to definition of subspace first. We write it here, definition first. Let a subset W of a vector space V, a subset W of a vector space V, okay, over a field F, over a field F is called a subspace. Is called a subspace of V. Subspace of V if W be a vector space over F. W be a vector space over F. Okay, and with the operation of addition, with the operation of addition and scalar multiplication defined on V. Scalar multiplication, okay, defined on V. Understood? A subset W of a vector space V over field F is called a subspace of V if W be a vector space over F with the operation of addition and scalar multiplication defined on V. So we also discuss, that means this one is the definition of subspace. Okay, to easily understandable, I think. Next we going to, that means in any vector space V, okay, V and in any vector space V and 0, okay, are subspace of any vector space V, any vector space V, okay. And then we also, that means this one is called zero subspace and this one is the vector space itself, okay. Again we also going to discussion of some following property, that means subspace satisfies some following properties, okay. We write it now. A subset W, a subset W of a vector space V, of a vector space V is a subspace of V, is a subspace of V, okay, if and only if and only if the following four properties hold, the following four properties hold, okay, the following four properties hold. First one, x plus y belongs to W, okay, whenever x belongs to W and y belongs to W, whenever x belongs to W and y belongs to W, okay, that means W is closed under addition. Understood? Now again we erase our portion and going to further discussion of that. Okay. Second what? Cx belongs to W whenever what? C belongs to F and X belongs to W. Okay, that means W is closed under multiplication, scalar multiplication, and obviously we write it here. W has a zero vector. Okay, and 4 we write it here. Each vector in W has an additive inverse in W. Each vector in W has an additive inverse in W. Okay, then that means this property, four properties have basic, that means properties, okay, related to that W be a subspace of V. If subspace of V, then these properties are satisfied. Okay, now we write it in a theorem form. So we erase that portion and going to be discussion of one important theorem related to that topics. Okay, we write this theorem first and then write the statement of the theorem. Let P be a vector space. Let P be a vector space. Okay, V be a vector space and W be a subset of V, and W be a subset of V. Okay, then what happened? Then W be a subspace of V. W be a subspace of V. What happened? If and only if and only if the following three conditions hold. The following three conditions. The following three conditions hold. Okay. What happened? For the operation defined in V. For the operation, okay, defined in V. First one is 0 belongs to W. Okay, second one, x plus y belongs to W whenever x belongs to W and y belongs to W. Okay, and number C, what happens? Cx belongs to W. Okay, whenever C belongs to F, whenever C belongs to F and X belongs to W. Okay, then what happened? We also write it proof here. Okay, we're going to proof of that. That means one subspace, one subset be a subspace of V then these three conditions satisfies. We're going to prove of that. Okay, so first we then start from here. If W be a subspace of V, if W be a subspace of V, then what happen? If W be a subspace of V, then W is a vector space, then W is a vector space. Okay, W is a vector space with the operation of addition and scalar multiplication. With the operation of addition and scalar multiplication and scalar multiplication. Okay, with the operation of addition and scalar multiplication defined on V. Defined on V. Okay, so what happened is here, hence condition B and C hold. Okay, hence condition B and C, B and C hold. Okay, not a problem at all. Now we're going to further discussion of that. So we erase that portion and going to further discussion of that. Okay, now here what happened, and there exists a vector 0 dash belongs to W such that what, such that x plus 0 dash equal to x. Okay, for each x belongs to W, for each x belongs to W. Okay, but also here x plus 0 equal to x. Okay, and then what happened, then obviously 0 dash equal to 0. Okay, so we think about that. So condition A hold, condition A hold. Okay, that means 0 belongs to W. Okay, next we discuss some portion, that means conversely we write here, conversely if conditions A, B, C hold, conditions A, B and C holds, then what happened, the discussion of the briefs, then W is a subspace of V, then W is a subspace of V. Okay, if the additive inverse, if the additive inverse of each vector in W, of each vector in W Okay, additive inverse of each vector in W lies in W. Okay, then what happened? Then but if X belongs to W, okay, then what happened? Then minus 1 X belongs to W. Okay, then what happened? Then minus X equal to what? Minus 1 multiplied by X. Okay, hence what happened? Hence W is a subspace of T. Hence W is a subspace of T. Okay, then W is a subspace of T. So next we're going to further discussion of that. Okay, that means we also goes to some that means discussion of some matrices. Okay, we erase that portion and going to further discussion of that. Here we write that means the transpose AT, the transpose A transpose, okay, of an M cross N matrix A, okay, is the N cross M matrix, is the N cross M matrix, okay, is the N cross M matrix and obtained from A by interchanging the rows with the columns, by interchanging the row with the columns, okay, with the columns, okay, that is what A transpose Ij equal to what? Aj, okay. Now we're going to further discussion of that. Further discussion is what? 1 minus 2 3 0 5 minus 1. This transpose equal to what? This transpose equal to 1 minus 2 3 0 5 minus 1. Okay, and here 1 2 2 3 transpose equal to what? Here 1 2 2 3. Okay, then what happened? Then we also going to discussion of that means symmetric matrix. Okay, a symmetric matrix a symmetric matrix a symmetric matrix is a matrix A, is a matrix A, okay, such that A transpose equal to A. Understood? Then what happened? Then obviously we shows about that. That means that what happened? Then W, the set of all symmetric matrices, is a subspace of M cross N. Okay, we write it in this way. The set W, the set W of all symmetric matrices. Okay, of all symmetric matrices in n cross n if. Okay, n cross n is a subspace of n cross n if. Okay, then also that means going to further discussion of that. This one is what we write it now. That means for any matrices, okay, A and B, for any matrices A and B, what happen, and any scalar AB and any scalar AB, what happen here, AA plus BB transpose equal to AA transpose and BB transpose. Okay, understood? I think not a problem at all. Next, we also going to discussion of another one. We erase our portion and we discuss that now. So, and obviously we write it in this way: if A belongs to W and B belongs to W, then what happen? Then A transpose equal to A and B transpose equal to B. Then what happen? Then A plus B whole transpose equal to what? A transpose plus B transpose equal to A plus B. Okay. Then what happened? So A plus B belongs to W. Okay. Next, this one is marked as 2. Next 3, what of which option is correct? If A belongs to W, then what happened? Then A transpose equal to A, and so for any F, so for any A belongs to this field F, okay, we have A transpose equal to A transpose. Okay, then A, okay, thus A belongs to W. Okay, next what happened? So we also discussed that the set of all symmetric matrices in n cross n matrix over some field F obviously become a subspace. Okay, so now we're going to discussion of another example related to that topics. Okay, obviously we know about that the diagonal matrices. Okay, we talk about that portion now. An n cross n matrix M is called a diagonal matrix, okay, if Mij equal to 0 whenever I not equal to j, okay, and all its non-diagonal entries are 0, that is that is all its non-diagonal entries are 0. Okay, then what happened? Then obviously clearly the 0 matrix is a diagonal matrix and all of its entries are 0. Clearly we write about that. Clearly the 0 matrix okay, clearly the 0 matrix is a diagonal matrix okay, is a diagonal matrix because all of its entries are 0, because all of its entries are 0. Okay, so 0 matrix obviously belonging to this set of all diagonal matrix, not a problem at all. So first condition is satisfied. Next we're also going to further erase our portion and going to further discussion of that. Okay, so we also known about that. That means if AB are diagonal n cross n matrices, okay, then whenever I not equal to j, okay, I not equal to j, a plus b ij equal to aij plus bij, and then what happened? Then this one, that means if I not equal to j, then this one equal to 0 plus 0 equal to 0. Okay, and obviously c of a ij equal to what? Equal to c of a ij equal to what? C of 0 equal to 0. Okay, for c belongs to this f, then what happened? Hence a plus b and ca belongs to what? Are the set of, are the diagonal matrices for any scalar, are the diagonal matrices. Okay, diagonal matrices. Then what happened? Then we're going to the conclusion of this result. That means the set of all diagonal matrices, okay, set of all diagonal matrices is a subspace of m n cross n f. That means the set of all diagonal matrices obviously becomes subspace of the set of all n cross n matrices over field F. Okay, we now erase that portion and going to further discussion of that topics. Okay, so we erase that portion. That means we talk about that the set of all matrices, symmetric matrices, are obviously from a subspace, and the set of all diagonal matrices obviously from a subspace. Now we also discuss more, so we erase that portion and going to further discussion of that. Okay, the trace of an in matrix. Okay, aim denoted by trace aim is the sum of the diagonal entries, sum of the diagonal entries of m that is what trace m equal to m11 m22 mnn. Okay, then what happened? Then the set of all n cross n matrices having the set of all n cross n matrices. Okay, matrices, set of all n cross n matrices having trace equal to 0, having trace okay equal to 0, obviously be a subspace of m n cross n f. How this one happen is subspace? Obviously 0 matrix, 0 n cross n matrix over f have trace 0, obviously belongs to this. Okay, then another one, if a n cross n f trace 0 and b n cross n f trace 0, then what happened? Then we know about that trace of a plus b equal to trace of a plus trace of b, then obviously 0. Understood? That means a plus b belongs to this set of all n cross n matrices and having trace 0. And obviously this one c belongs to f. Okay, then ca n cross n f, then what happened? Then trace of ca equal to what? Trace of ca equal to obviously we talk about that. That means c is some c plus c is then ca11 ca22 cann. Okay, c common, c of trace of a, so equal to 0. Understood? So c of a obviously belongs to the set of all n cross n matrices trace 0, and obviously a b, if set of all trace 0, then a plus b obviously belonging to this set of all n cross n matrices having trace 0. So I think all are understood that portion, and so the set of all n cross n matrices having trace 0 obviously be a subspace of the set of all n cross n matrices. So today we stop here. Okay, we also discuss so many important topics related to this subspace. That means we are also going to be discussion of one theorem, obviously is definition of subspace, and give some familiar example related to this matrices. That means they become subspace. How they become subspace we also discuss. That means in a fascinating or simple way. So all I understand that topics. I think today I'll stop here. If you get this type of video, please subscribe my channel and obviously follow my channel and follow this video and obviously gather knowledge. And if you gives like, please click on like options. If you have any question, comment, suggestions, write it in comment box. So today I'll stop here. Okay. Thank you.